Hello everyone, welcome to the 6th tutorial of ECON1310, Introductory Statistics for Social Sciences. Today we'll be talking about sampling distributions, and it's really interesting because every time you think about statistics, most of the times there might be some sort of sample or sampling happening. So we're finally touching it and discussing how to think about it. But before everything, let's go to the admin part. The LBRT second attempt was just open this morning at 9 a.m. So I would strongly suggest you, if for any motive, but particularly if you didn't get the highest possible score, which I believe is 26, to do your second attempt. And like first, my suggestions would be have a look at your first attempt, see what you got wrong, try to fix, try to solve it again, to understand what went wrong, because there's a big chance that your second attempt will be better. So I think everybody should do, even for in a matter of attempting to get either a better score or trying a little bit more for practice. A few details. So second attempt, same thing as before, 90 minutes, 1 hour and a half, and it will be open until tomorrow, Friday, 4 p.m. This is Brisbane time. Of course, have a look how it converts to where you are. And wow, if I were you, like, check what you did wrong, do the exercise until you get everything right for your first attempt. Then you go for a sleep, wake up tomorrow, relax, have your breakfast, go to the toilet, and then come and start your second attempt and try to get the best score you can. Other than that, we will consider only the best score. So you have nothing to lose during your second attempt. So it's really worth it. I strongly recommend doing that. Preparation. If you haven't yet, do the practice LBIT. It's always a good idea. And I think that's about it about LBIT that I'll talk about. Also, your CML3, the first attempt, is also open. It's actually open since Wednesday, since yesterday morning, and it will close on Monday. So I hope you guys are already giving it a go, trying. In the case of the CML only, you feel free to discuss with all the people, see if you guys can solve together, just in case there's any doubt. For the LBRT, there's no discussion. You have to do by yourself. And for back here with the CML, no, you have a long time. You don't need to submit it immediately. You can close it, save everything, close, come back tomorrow. But the most important, don't forget to submit before the Monday 4 p.m. This is something that is very can cause some confusion for people. LBRT, the previous one, only 90 minutes. Let me also get a little bit of a thing here. Only 90 minutes. And the answers submit automatically by the end of it, by the end of the 90 minutes. Then CML, you can use many days to solve, but the answers don't submit automatically. So you need to go there and click submit. Don't think just because you were saving that they were submitted by themselves. Okay, just trying to make it a little bit more clear. Any question before we start the tutorial? I will open a chat, double check. Nobody sent a message just yet. Feel free to open your mic if you'd like, or send a message in the chat. I think in general, okay. Are we able to check what questions we got wrong in the LBRT? I understand that you get your score, but it will only be opened on Monday. Let me see if it was in the announcement here. Reminder, you'll be able to view both your score and feedback on Monday only. Unfortunately, you cannot see what you got wrong. Sorry. So part of what I said might not be right. Wasn't completely right. Yeah, it can be. You might have to look for what you might have done wrong. So maybe an attempt of solving the exercise again, see if something you missed or you were a little bit confused, but you won't be 100% sure of what you got wrong. Sometimes it's possible to, depending on your points and depending on how much each question was worth, maybe you might be able to find, but I'm at the moment, I can't remember if you guys can see how much each question is worth while you're solving it. If someone remembers, please let me know, send it in the chat, because I can't remember if you can see, therefore, not sure if that's possible. I know that some questions are worth different amounts, so sometimes it's possible to see what you got wrong. Yep. Anything else? Perfect. All right, so let's go. So today, sampling distributions, tutorial 6. And at the end of this tutorial, we should be able to describe characteristics of sampling distributions for sample means and sample proportions. Explain the importance of the central limit theorem. Calculate the z-score for particular values of the sample mean or sample proportions, and calculate the probability of obtaining particular values of the sample mean or sample proportion. All right, let's go. Question 1. These first questions will be the first question, first 2 items will be quite theoretical. So let's go. Explain the theoretical development of the sampling distribution of X bar. Define the mean and variance for this distribution. Look, we have been looking at the normal distribution, and usually we have the population. In this case, is the pond with different lengths of fish, but we had different exercises talking about different things, right? Let me get this little guy here. So this is the population. We'll get a different color. And well, you can get one sample of it. The thing is, let me get one more thing. When we're dealing with just one, just what we did last week with the normal distribution, we were talking about grabbing just a sample of one. This can be a little confusing, but like just talking about one. And this is how this one is distributed. It could be, there's a big chance that the length of this fish would be close to the mean, and a smaller chance there will be either very small or very large. This changes a little bit, and we for the previous ones we used the seagull holding one fish. Then we're moving to the pelican, and this is the sampling. When we're talking about a sample, it's a few fish together. So now what happens is the following. Because we get a few fish, there is a much larger chance of the average length being closer to the original mean than it being very far, like the average of the sample being too small or being too large. Let me click once again, and you will see how it works. Look at that. We were using this formula to calculate the Z value, and it might look a little bit uglier here, but I'll try to convince you that what we're doing is very simple. And we have always been using this formula, but we have been using this formula for an n equals to 1, right? So this looks ugly, like you have a mu, you have a sigma, but in fact, what we're doing make our x become a z, we're just doing two things. We subtract the mean, and then whatever we get, we're divided by the standard deviation. That's it. Subtract the mean, divided by standard deviation. No, a big thing about it. But the only thing that changes now that we're talking about a sample is that n is not 1 anymore. N is the size of the sample. For example, it could be 10, it could be 100, it could be 200. So look at this guy here. This is the size of the sample. It's the lowercase n. Look at this guy, x bar. Looks very similar to our x, but x bar is actually the average of our sample. So when we're looking at the fish, we're talking about, we get a bucket with 20 fish, n equals 20. X bar will be the average or the mean length of the fish inside of the bucket. It's not one individual, neither the minimum nor the maximum, the mean, okay? Mean or average. Does that change a lot from what we're doing? Think about it. So if n was 1 until the previous tutorial, look at this. If we get the same thing here, this divided by the square of 1, which is exactly the same as here. If it's square of 1, it disappears because it's 1, right? Square root of 1 is 1. The mean of 1 is actually its own value. So if you get a fish, the mean length of that sample of one fish, it's actually the length of the fish. So it's the same thing that we were doing. So ends up that this uglier equation is just a tiny bit different from this less ugly equation here, which is actually a very simple thing. We are subtracting the population mean, and then we're dividing by the standard deviation. And the standard deviation, it's something that changes the bigger the sample is. So the bigger the number of n, the higher it goes. The smaller this is because it's in the, it's in the denominator, right? It's the bottom part here of this bar. So the more bigger your sample, smaller your standard deviation. And I think that's it for this one. Let's keep on moving before I spend too long talking about this one. Guys, and feel free to open your mic or send any question in chat. Let me see. Nobody sent it yet. Yeah, let me know. I will click. Let's go to the next one. So this was an explanation about how it works when we're dealing with a sample, which is bigger than 1, right? The other thing we want to talk in this question is state the central limit theorem and explain why it's important in statistics. So the central limit theorem, it allows us to assume that as long as you have a large sample, you can consider that the distribution is normal, which is what we've been assuming in the previous tutorial. We were saying, oh, assume that the distribution is normal, or the scientists believe that the distribution is normal, or whatever, right? So look at here. This is from your slides. Central limit theorem states, as the sample size gets large enough, as n increases, the sampling distribution of x bar, so the sampling distribution of the sample mean, becomes approximately normally distributed, regardless of the shape of the population variable distribution. And I will show an example later. So how large is large enough? And that's what we're talking from here on. For the sampling, there's kind of a magic number, which is n being bigger or equals to 30. So 30 or bigger usually is enough for us. So for most population distributions, the CLT states that n bigger or equals to c, the sample distribution, that's what they're talking here. So long, it doesn't matter the distribution of the of each single observation, as long as you have 30 or more, you can make an assumption that it's normally distributed. Okay. And look at a very nice example, very easy to picture. Rolling a die. And if it's not biased anyhow, rolling just one will give you this distribution. It's exactly the same probability of getting 1 or 2 or 3 or 4, 5 or 6. If you roll two dice, then look how it changes. It becomes this kind of little house format here. It's just a kind of triangle for two of them. Why is that so? There's just one way, one combination for you to get 2, which is getting 1 and 1 in each die. But there are many ways of getting 7. It can be a 1 and 6. It can be a 6 and 1. It can be a 2 and 5, 5 and 2, 3 and 4, 4 and 3. So the chance, the probability of getting 7 is 6 times larger than getting a 2 or getting a 12. And then if you add a third one, look how the distribution starts moving, and then a fourth, and then a fifth, and look how it looks like a normal distribution now. And this magic pretty much happens with any distribution. So you can look on Google, and the more and more observations you keep adding on it, the more it looks like this shape here. All right. But then you might be asking, well, but what about the sample proportion? Do you remember the freaky fish? If you're watching the lectures, particularly, was my favorite of the 3. So we have the seagull, we have the pelican, and then we have the freaky fish. So in this case, the case of the freaky fish, there are 2 rules we have to follow. Let me draw them. See. So either P will have to be equals to 0.5. So the population proportion will have to be this one. And this is rare to happen. Or we will need the size of our sample times P, which is the population proportion, to be bigger than 5, but also the opposite. Sometimes you will see this guy called Q, which is n times Q, or n times 1 minus P, to be bigger than 5. So that's how it works for the sample proportion, right? Let me clear it here. Any question before we go to question 2? Okay. Oh, sorry. Harry, I'm just seeing your question now. COT allows us to assume that the sample mean is approximately equal to the population mean, given that the sample size is sufficiently large. Amazing. Very good explanation. Thank you, Harry. Let me see if there's any other question. I think that's it. All right. So I will let you guys work a little bit. I'll have a poll for this one. Let me launch it. Question 2. Launch. Hope you guys can see. And I will read. You have a little bit of time. Three questions there. So I will also click. So people who are watching later, this time I remember to add the poll there, so you guys have an idea. Give it a go. Try to see if you can answer it at home too. But let's go. According to Nielsen Media Research, the average number of hours of TV viewing per household per week in the US is 50.4 hours. Suppose the variance is 139.24 hours squared. And a random sample of 42 US households is taken. Find the probability that the sample average is. So find the probability that the sample average is more than 52 hours. This would be the first one. And with this, you already, I think it gives you a chance to start thinking about what we're talking about. Let me see how the poll is going. I have, at the moment, 11 answers. Pretty good. 13 answers. Yeah, I will give you another 45 seconds. Let me read the question again. So, according to Nielsen Media Research, the average number of hours of TV viewing per household per week in the US is 50.4 hours. Suppose the variance is 139.24 hours squared. And as a random sample of 42 US households is taken. Let me go back to the poll. I have 21 answers out of our 24. I think that's it. 2 minutes. I will end it now. So share results. Look, can you see? So I shared the results. For what symbol would you give to the value of 50.4 hours? So we're giving a mu. Congratulations, guys. You got 15 out of 21. Got it right. Let me click here. It's a mu. So we're talking about population. Look at that. According to Nielsen Media, I don't know if you guys can hear a noise. I'm sorry to interrupt, but I'll be back in a second. Just give me 1 second. Apologies for that. There's something happening outside of the apartment, so I closed the door. It should be better now. So congrats, guys. Back to where we were. According to Nielsen Media research, so it's not a sample that we have right now. It's a research that happened in the past, so it's probably talking about population. The average number of hours, 50.4, amazing. So what symbol would you give to the value 100? Oh, I put 49.24. I'm sorry for that. It's a 139.24. And you guys said sigma squared. Good job. Very good job. This one could be trickier. Some people might have thought, some people thought it could be the sample variance, which is, I understand, it is tricky here because it's closer to what we're talking about, the sample. But to be the sample variance, they would have to have the word sample in there. So yeah, that would be a prerequisite for this one. Because I mean, it's tricky, but you say, suppose the variance is this, hours squared, and then a random sample of 42 US households taken. So despite being very close to the talking about sample, it's not saying it's the variance of the sample. Okay, just this one for the second one. And finally, the third one. What symbol would you give to the value of the 42 households? It's a small n, very good. 10 out of 21, got it right. This is the size of our sample. And now we're talking about this part here of the screen. Very good job, guys. I'll stop sharing. Let me have a look if there's anything on chat. No, good. Let's keep going then. So variable of interest, it's our TV viewing time per week. That's what we're talking about. Mu 50.4, sigma squared, the variance by the population variance. That's what sigma indicates. 139.24 and equals 42 households. And we're asking, find the probability that the sample average is more than 52 hours. Let me see. Look at that. Let's put it in our distribution. We're talking about sample. So you will see this little guy here. It's not X anymore. It's X bar. So the probability that the sample average, if we go back a little bit, sample, mean, sample, average, X bar. Okay, let's go. So let's draw it. The mean we have, mu, the population mean, 50.4. And then we're looking for X bar, the sample mean, and we're asking about being a 52. We put a bar here on 52. It's to the right because it's bigger than 50.4. And we want it bigger than. So paint this area here. That's the probability that we're talking about. But then we asked, can we do a Z transformation? Do you remember what was the rule for the Z transformation? Can anybody pop in the chat? What do we need to check in this situation? It's a very simple rule. It's the one that we saw before the freaky fish. Let's see. So what we need to check in this situation, because we're looking at the pelican here. So the sample distribution, we just need to check if the sample is bigger than 30. So let's go. Look at that. Oh, I clicked. So, and we're checking based on the central limit theorem. If n is bigger or equal to 30, n is equal to 42, therefore bigger than 30. So we can use the Z transformation. And so let's do it. I also copied here. This is the summary of the formulas you have in your slides. I think it's very nice. Pay attention that these are all the same thing, all the same equation. It's just arrange it in different ways to make your life easier. So instead of yourself flipping around and multiplying and subtracting, Carl already prepared a slide with everything for you. So if you're looking for a Z, here it is. If you're looking for a mu, here it is. If it's X bar, and if it's sigma. Okay, just trying to make it as easy as possible. So we're going for a Z transformation. Removing. Remember, what do we do in the Z transformation? We subtract the mean. But let me use a little bit a pen just to indicate what's going on. So we subtract the mean and we divide it by the standard deviation. But now we're talking about the pelican. So we're talking about sampling distribution. So our sigma, our sample standard deviation, is divided by the size of the sample for the number of individuals we have in the sample. So it's a little bit different calculation, but let's go. This is what changes. Let me click. Look at that. Our sigma was here. Another thing to pay attention, I didn't mention. So this is the variance. And I should have written squared in that. Let me fix it. This is a good chance, good opportunity to move. It went all the way back to fix a few things. This hours should be squared. Okay. It will be wrong for the next few slide. Sorry for that, but I think it's good that I took all the attention. So 139.24 hours squared. So for the next one, it's wrong again. Sorry. But let's go. Look, how do we get the standard deviation out of the variance? You just take the square root. So 139 divided 24 square root of it, and then divide by the square root of n, which is our sample size. And then you get this number here. If you want to check, let's do it in the calculator. 139.24 square root is this little button here. Then divided. Now I will open a bracket just to make sure. 42 and then square root again. Close my bracket. This is the square root of 42 equals 182.07795 blah 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 blah. But we try to, because this number will be dividing all the things, we try to use a few decimal places so you can be very precise when we're looking for a Z. Okay. So 1.82077. This is just the standard deviation. This is just this number here and just this one here. Let's go to do the rest. So back to what we were doing. Now we're doing the Z transformation. The probability that the Z is greater than this area here. So let me see. we are now replacing the values of, sorry. So X bar, we know we're dealing with the 52 hours. Mu, we have the 50.4. So it's positive because it's in the right side. Then we have this big, large number here for our sample standard deviation dividing, okay? Equals to, if we want to do, let's do it again. And the calculator, I think just the first ones, let me show you, just in case someone is having any trouble with the calculator on Windows. So subtract equals 1.6. Pretty much a positive number is what we expect since we're dealing with the right side. And then divided by that massive number. So 1.8207795 equals 0.8787445. Now we're going to look at the Z table. So we are rounding to 2 decimal places. All right. Perfect. Let's go. Let's do it. Now I'll ask your help. 0.88. Can you guys pop on chat the value for 0.88, please? Let me write it down. We want 0.88. Do you guys remember how to do it? It's been 2 days already. do you know if you forgot? Do you guys remember how to get the 0.88? Can someone please check on chat? Amazing. Yeah, thank you so much. Beautiful. Great job. So there you go. Very good. 0.88. And let's go. So let's use this number. So we know that this probability is 0.3106. But as you remember, this is the distance, kind of the area, not distance, sorry, the area between the mean and the thing. So it falls inside of this area, which means, which means the rest here is just 0.5 subtracted off this amount, right? So this is what we got. So basically find the probability that the sample average is more than 52 hours. The probability is 0.1894, which is very close to 19%. All right. If you guys have any question, please open your mic or send a message. Yeah. If otherwise, I'll keep going. Let's go. Now, same thing. Let's check if the probability that it's less than 47.5. I changed here. You'll see a little difference. So probability that our X bar will be smaller than 47.5. We already know that we can do Z because the values of N is still bigger than 30, so we're still fine with it. So Z is down here, the 0 is here, 47.5 is smaller than 50.4. So it's to the left. It's probably, so Z is probably going to be a negative number. And that's it. Let's go. Let's continue doing this one. So Z transformation. Once again, as you can see, we're using this formula to find Z. Pretty much the same thing we did. Get the number we're looking for, subtract the mean divided by standard deviation. Standard deviations is still the same. So we're just doing this little thing here. Think just once again to do the calculator, use the calculator. So, oh no, I'll have to change. Okay, 47.5 minus 50.4 equals minus 2.9, which makes sense since it's since it's to the left of our distribution, right? Of our distribution mean. So now let's divide about the large number. 0.7795 equals minus 1.5927 and blah, blah, blah. But for our Z table, it's just 1.59 is enough. So let's go. 1.59. Can you guys please put on chat how much it is? We're looking for minus 1.59. I will use a different color, a lot darker color. Excellent, very good. There we go. Amazing. Thank you so much, guys. So you were right. One here, 4441. So this is the value. So once again, we have it to the left of the mean. It's smaller than the mean. So this area is this is the area between the mean and the Z value that we're looking for. So we just subtracted from 0.5 and we get a 0.0559 there. If you guys have any question, please send a chat or open your mic, but I'll get going for 36. I think we're doing well with this exercise. Please let me know if by any chance I'm doing it too slow or too fast. If I'm speaking too fast, I can try to just speak a little bit slower. And we've been using the whole time of the tutorial. We haven't been late, so I don't think we're doing too slow. But for some people, if it's too easy, maybe it might sound a little bit slow, but I'm trying to like attend people who might have more difficulty with it. But yeah, let's go. Mouse, I'll close this one. All right. Oh, did I skip anything? So this might be a little bit more challenging, but look at it. Suppose the population standard deviation is unknown. So this disappears. Standard deviations and variance, they walk hand to hand. One is the square root of the other. So standard deviation is the square root of the variance, or the variance is the standard deviation squared. So if you know one, you know the other. If you don't know one, you probably don't know the other. Okay. So this is unknown. Therefore, variance unknown. If 71% of all sample means are greater than 49 hours, and the population means is still 50.4 hours, and you can see here, what is the value of the population standard deviation? So we know, remember, if you know the probability is 71, therefore you can paint in our graph the area, right? Look, we know the 49 is less than the mean. I don't know exactly where it sits yet, but I know it's to the left. And it is, let me see, 50s. All samples are greater than 49. Okay. And you also use it to the left, and it pans into the end because this is 71% of all samples are greater. Okay. We also would be able to know it's to the left without knowing the 49 because it's telling us the 0.71. So we know it's bigger than 0.5. Therefore, it's crossing the mean. So there is, everything is, there's a 71% that it's greater than some type of number. Then you know, like, okay, we're talking about greater. So we're talking about the right side here. And it's more than 0.5. So it's probably taken a little bit of this left side too. Okay, but that's not necessary for this one. They specify the 49, which is smaller than the mean, 50.4. And this is the probability. Look how it looks. Probability of our X bar being bigger than 49 is, we don't know the standard deviation yet, but we know as we have 0.71, right? Okay, I'll keep going. We know we also know we can do Z transformation because we have 42 households. But in the Z transformation, remember the values we get over there in the table, they're not taking in, it's up to 0.4, 0.5. So what we'll be looking for, as we did 2 days ago, is just looking for the 0.21 Z transformation, B equals to Z, and etc. Look at that. Putting it back in the formula, you have 49 minus 50.4 divided by, we're still using this guy here. So X bar minus mu, X bar minus mu, right? X bar minus mu. And then the sigma we're looking for divided by square of n. Here it is, and it's the size of our sample. Equals to 0.21. Let's have a look in the table. 0.21. All right, I put it there. This stuff from here on, I think we'll have everything there, unless I missed it anyhow. Can I please have on chat the Z value in this case, not the area? Let's look for the 0.21 and see which one is closer. Amazing, very good job. Exactly, look, 0.21, very good. 0.21, the closest one we have is here. And you might question yourself, well, it could be maybe this one somewhere around here, but it's still much closer to this one. It's like there is a 12, like 0.0012 distance from this one, but there's a 23 distance from this one, 0.0023. So because it's closer, we will use this one. And then you do the thing, 0.55. Excellent. Great job, guys. So we only do the average when it's in the middle, exactly in the middle. There we go. Let's go. So minus 0.55, very good to, I'm seeing the minus here, I didn't mention, but we know it's to the left, so it has to be negative in the Z. In the Z transformation, it has to be negative, because this is 0, to the left is negative, okay? So minus 0.55, and look at what we're doing. When we're looking for sigma, this is how these guys here become really handy, because you could just plug the values in this first formula and you would get the same number, but you had to move things around a little bit. Look, these slides here, they make it very easy because they already isolated your sigma. So you just plug in the numbers, our X bar 49, then our mu 50.4, our square of n, it's 42, square of 42, which is here, and Z we found minus 0.55, it's there, so you just solve it. Should I check? I will give it a go here in the calculator. So 49 minus 50.4. So I'm solving from inside out, okay? Equals minus 1.4 times, I will open 42, then squared, and then I'll close, equals minus 9.07. Now I want to divide by a negative number, and this sometimes is annoying on this Windows calculator, but divided, then I'm going to open the bracket, minus 0.55, then I'll close the bracket, so I got a negative now, equals 16.4964. And then a lot of things later, I'll just cut short and on 4 digits. And that's it for question 2. Do you guys have any questions regarding this one? Let me open chat, see if I missed anything. You guys are killing it. You're doing really well. Let me know if you need anything. So in this case, we're talking about the standard deviation. So it's important to remember that it's 16.4964 hours. So it's not a proportions. We don't use units because it's just a percentage. It's a number divided by another number that has the same units. So it's a proportion. But when we're talking about standard deviation or mean or sample standard deviation, sample mean, sample variance or variance, then we have units. So don't forget to mention the units. Okay. If they were asking variance, don't do one mistake. Don't forget it's hours squared. But in this case, they are asking standard deviation, so it's just hours. All right. We'll keep going. Let's go to question 3. I'm quite sure question 3, we also have a poll. So let's go for it. This one, we will be asking, I'll be asking also the variable of interest, which is usually a tricky question. I see usually the results, the answers are more distributed around the options. I'm not making your life easy with these questions, but try to think what the question wants to know. So what's the variable of interest there, right? Let me read the question. A travel association survey asked travelers about the purpose of their visit. 19% responded it was to visit relatives. So relatives, usually family, right? If you're not sure. Suppose 950 travelers are selected at random. What is the probability, the proportion who say their reason for visiting relatives is more than 22%. Let me fix a little bit here, the way it's written. What is the probability that the proportion who say their reason is for visiting relatives is more than 22%? Okay, so we have a few numbers thrown there. We have a 19%, we have a 950 travelers, and we also have a variable of interest that I put there. Let me see how many people answered. I have 11 answers only. We have a lot of people who can still have the opportunity to answer. I'll give you another 30 seconds. So a travel association asked travelers about the purpose of their visit. 19% responded it was to visit relatives. Suppose 950 travelers were selected at random. What is the probability that the proportion who say their reason is to visit relatives is? What is that probability? And then we start calculating more than 22, between 15 and 20. So I have only 13, 14 answers now. Do you guys, do you need more time? Maybe the last few ones? All right. So I will close in 5 seconds. 2, 1, and that's it. I will share the results. I think maybe because I started with the variable of interest, it gets a little bit more tricky. I understand that. So this is the answer here. Now we're talking about this beautiful freaky fish. And look how we interpret. So what is the variable of interest? They are thinking about the proportion of people who visited relatives. And I can see it was very well, a very spread in our, there's the purpose of the visit. It's not exactly all the answers I offer there. They're kind of right, but not exactly our variable of interest. So we got 5 people choosing the proportion of visiting relatives. I would say perhaps this question could have been written a little bit better to make it more clear. And after that, so this is what they're looking for. So what does the 950 travelers, what symbol would you give for it? It's little n. Perfect. 13 out of 14 of you guys got it right. And what is the symbol you would give for the 19%? And some of you, 5 out of 14 said P, and 6 out of 14 said B hat. And this is tricky. I agree with you. This is very tricky. I can see the correct answer is P, and this is why. So a travel association survey asked travelers about the purpose of their visit. 19% responded it was to visit relatives. This is not talking about the 950 that we're taking later as our sample. This previous survey probably was every single, so it would be a population, or maybe it was a different thing, or it was less than 950. We don't know. We don't have that information, but it's a number that we had in the past. Our sample here is the 950 travelers. So that's what we're calling a sample. That's that I shaded in light blue, like somewhere between green and blue. And the only thing is the N. The other one we have, it's kind of a population, but very tricky question. Yeah. So I will stop sharing and I'll get going with this exercise. And close. Yep, I share the results you guys saw. All right, let's go. So suppose 950 travelers are selected at random. What is the probability, the proportion who say that their reason for visiting relatives is more than 22%? I put the summary here, but so variable of interest, proportion of visits, and P equals to 19%, it's 0.19. And what is the, okay, P hat, it's what we're looking for. Before we were looking for the X bar, sample mean. Now this is the P hat, sample proportion. We know P, we have a P, we were looking for the P hat. So the probability that P hat is bigger than 0.9 at 0.22 or 22%. Let's see. We put it in a distribution. I should have fixed this one. It's not X bar, it's P hat. Sorry for that. And look at that. 0.22 is bigger than 0.19. So it's to the right, and I painted there. But we still haven't done the transformation. Let's click. Can we do a Z transformation in this case? Do you remember the rules? And now we go for another poll, pretty short one. It's just a yes or no poll, and have a look. I already gave some advice. I brought in the slide that we saw before. So we have the criteria here, and these are the questions. So I will move this guy. Let me close this guy. So you guys have a chance to see the numbers, so you can make a little bit of the calculation and times P. So the questions are, is P equals to 0.5? And this P is the population mean. If not, is N times P bigger than 5? And this is important, this is an and. Is N times 1 minus P bigger than 5? If both are correct, then yes, we can do a Z transformation. Otherwise, we cannot do a Z transformation. We cannot assume that it's normally distributed. Therefore, we cannot do the Z transformation. Let me have a look how the poll's going. Mouse. I have 10 answers. Let's see, 11. I know it takes a little bit more thinking on this one. I'll give you guys another 30 seconds. 12 answers. But we have 24 people, 25 minus 1, that it's me. So have a look. This is what we're checking. It's just yes or no. The questions are, is p equals to 5? Is n times p bigger than 5? Is n times 1 minus p bigger than 5? And can we do a Z transformation? I have, what am I doing? Sorry, I spoiled a little bit. If you're paying attention very quick, you might have. You probably got the, so 19, that's very good, guys. Think 20, thank you so much. I will end the poll and I'll share the results. So very good job. In general, you got everything correct, got everything right. So although P is not 0.5, and how do we know? P, we know here. Our population, based on the previous survey, was 0.19. So not 0.5. So we got to know here. Then we went to check the rest of the things. Because our sample is really large, 950, multiplying by 0.19 or multiplying by 1 minus 0.19, which is 0.81, gives us massive numbers. And therefore, it's a yes. Now I start getting a feeling why you see, like when people are newspapers doing a poll for elections and this kind of things, they interview like 2,000 people, 5,000 people. This is what they're doing. They are making sure there's, well, it's not exactly, I think it's a little bit of a stretch, but having a lot of people, having a very large sample, make your estimates more precise. Okay, it's a little bit more complicated than that, but we will get there in the future. So let's go. We can do a Z transformation. So let's do it. Just same thing here, but this is a Z. So let's find. We're using the same. Look at the formula here. Not exactly the same. Since we got a yes for using the Z, then we can use this little summary that we had, as we had for the Pelican. And we will use this first one here. Look, it's relatively, it's a little bit different, but it's pretty much the same as we had before. So instead of the X bar, so the sample mean, we have the sample proportion. So it's the P hat. Very simple. Instead of mu, we had the population proportion. So instead of the population mean, population proportion. Doesn't feel too different. And instead of the sample standard deviation, we have the sample standard deviation, but it's the P hat over there. And look how we calculate it. Instead of having this, sorry, let me say it again. Sigma X bar, we have the sigma P hat, which is still the sample standard deviation. And it's just a little bit different the way we calculate. We have a square in the bottom, square of n, but we also have a square on the top, which is P times 1 minus P. Or sometimes you will see this part here written as Q, the 1 minus P. And it's pretty simple. As we have the value of n and we have the value of P, we can click. So we have a number, and we here for the standard deviation, sample standard deviation. And then we go for our we can replace everything in this formula here, getting this guy. After transforming doing the Z transformation, we have Z is equal 0.22, which is this guy, minus 0.19, which is this guy and this guy, and divided by the standard deviation that we got before here. All right. In the end, we got 2.36. So you guys ready with your keyboards? Let's try to find in our table 3.36. That's the number we're looking at. We're looking for, can you guys please put on chat how much you find for this one? So 2.36. you will see that I sliced the excellent. Thank you very much. Good job, Daniel. You'll see that it's sliced in a different way here, so we get the bottom of the table. So 236 went a little bit off road there, but it's somewhere around here. Great job, guys. You really know how to use the Z table. For the ones that didn't get it right, everybody who popped it on chat got it correct. But if someone tried at home and didn't get it right, have a look what you did wrong and how people got to this point here. Okay, let's go. Thank you so much for your participation. So replacing it at probability, once again, remember, it's the area that touches the mean. So this is where the value goes. So the little guy here, it's what we're looking for. Actually, I draw it pretty large. If you want to be very precise, look, it should be a little bit smaller because it should take just 1% of the area. And I think in my drawing took almost half of the area. But yeah, that's a little bit, it happens a lot of times. So here it is, 0.0091 is the answer. If you guys have any questions, please feel free to open your mic or send something on chat. I'll keep going. Now, same thing, but now between 15% and 20%. So we have the distribution, the number of the sample size and the proportion are still the same. So we already know we can do Z transformations, right? I kept everything, I kept the Z over there. Let's, once again, the X bar shouldn't be an X bar, should be a P hat. So apologies for that. We'll fix it later. And we want between 0.15, which given the population mean is 0.19. We know 0.15 is to the left and 0.20 is to the right. So one of our Z values will be negative, one of our Z values should be positive, right? Let's keep on going. I will paint it. We could try to do something a little bit more proportional. So the 15 should be much further than the 20. And doing the Z transformation using the same thing. Pretty much say here, the same result that we had before. And then we have replace everything here. So the P hat is what we're looking for. T is the population mean, 0.19. See how it replaces beautifully. Now we have two of them to look in a table. You guys ready? So I think you guys dominate already the Z transformation. So let's go. First, we're looking for the minus 3.14. Let me open the chat. Could you guys please help me find how much it is? 3.14. Excellent. Very good. Thank you so much. Amazing. Very good job. So let me click. Well, let's draw first. 3.14, 3.1. You remember the minus doesn't matter here. And the 4 ends up with this one. Great job, guys. So now let's look on the other side. It's in the beginning of the table, kind of. 0.79. Can I have the area for the Z value? 0.79, please, on chat. $0.79. Amazing. Great job. Yes, thank you so much. Excellent job. So let's go that 0.7 and then 9. So here, this guy is, well, this was terrible. Yeah, there we go. Excellent. Good job, guys. Let's go. Put it up. There it is. So in this case, as you remember, we want this area. It shows the area from one side. The area that touches the mean. Because we have one on each side, we're just adding them. So it's just an addition, and it gets us to 0.7844. Cool. That is it. Now we're going to the next one. The next one, tiny bit more challenging, little bit more challenging. Let's go. What is the value of p hat below which 5% of all sample proportions lie? Value of p hat. So we still have 950 households as our sample size. We still have p equals to 19%, considering the survey, and we want what p hat. Where does it sit? So just 5%. Below which 5% of all sample proportions lie. We know if it's just 5%. Therefore, it has to be somewhere around here, right? So just 5% sits to the left. So value below which. Well, you get this from below, okay? So it should be somewhere in here, and the rest is the other 95%. Let me click on the mouse. So I will draw it here, but these are not Z values or the values of p hat. These are areas. That's why this time I changed it to red. And this is the area with 0.5 minus the 0.05, 0.45 here, right? So if you want to use a Z, that's what we're looking for. Okay. Z transformation. Look how handy the rearranged formulas are. Look what we have there. Instead of using the top one, we're already going for all that. We're looking for a p hat. So we already have the sigma p hat, which is our sample standard deviation. Why do we have it? Because we know n and we know p. So we know this guy. We know this guy. But we still don't know z. How can we find z? A little bit of advice here. We can move this guy here. We know the area. We know the area of this guy. So if we find this area, we will know this little area, and then we have our z. Pretty much we don't even need, we know the area already of this one. We just need to find how much this guy is. Okay, so let's go. Which one are we looking for? I think I shouldn't have said it. I kind of gave an advice, but I want you guys on chat to tell me the area we're looking for. I'm sorry, the Z value we're looking for. And I will leave it for you to interpret. Oh yeah, sorry, the area is 0.4. Oh, sorry. Yeah, I gave it up. Sorry. Now let's look for the Z value. And good job, Harry. Apparently, it's something that happens often, right? I gave out the answer before I give you, before I give enough time. But yeah, great job. We're looking for the 0.45, and let's look for it. It increases this way, so 0.45. It's here and here. Tricky. It is exactly in the middle. So 0.4495 and 0.4505. Both of them are 0.0005 distant from what we're looking for. So how do we work with it? Let me Where's the middle? So we found that both of them are in the same line. So we know it's a 1.6 something, but we have 1.4 and 1.5, the 0.04, 0.05. So we just get the one in the middle, and we end up 1.645, which sits right in the middle here, because our area was exactly in the middle. Okay, so we're going to work with 1.645 as our Z value. Is it positive or negative? Can you guys put it on chat? Positive or negative? Nice, good job, excellent, thank you, fantastic. So look, it's to the left, and negative 1.645. So there we go. We multiply, replace all the, now we have all the variables, replace everything, and we get 0.1692. Great job. Fantastic job, guys. Any question? Feel free to send, if you have any questions, send them on chat or open your mic as always. But let's go to 4, given it's already 5:11. Let's go to question 4. A doctor believes that 80% of all patients having a particular disease will be fully recovered within 3 days after receiving a new drug. I have poll for this one too. I have this and another poll later. So let's go. I hope you guys are still strong there. Let me click. I think I'll show the poll. Yes. So I've sent you guys. So a doctor believes that 80% of all patients having a particular disease will be fully recovered within 3 days after receiving a new drug. A simple, and to answer our questions, let's have a look at A simple random sample of 20 medical records will be used to develop an estimate of the proportion of patients who were fully recovered within 3 days after receiving the drug. If a data analyst suggests using a normal probability distribution to approximate the sampling distribution of p-hat, what would you say? Explain. The first thing I want you guys to work on is, let's try to understand what is our variable of interest. So what are we trying to measure? You have already a few little bit of advice there with a freaky fish. We're talking about proportions, right? So have a think about what are we trying to measure, and what are we talking about when we have the, what symbol would you give for the 80%? Let me see how many people answered. And what symbol we're giving for the 20 medical records. I have 14 answers. Very good. 15. I will close it in another 20 seconds, so you guys can give it a go. I can see very good job. Yep, 16 answers. I think this time I kind of gave out, after some time, I kind of gave out number 1, right? Well, seems like something that happens a lot. And I think that's it. I have 17 answers. Last few seconds. 3, 2, 1, and poll. I'll share the results. So first, what are we talking about here? Our variable of interest. We are talking about how many, what is the proportion of people who are fully recovered, right? A proportion of patients who are fully recovered. We have some doctor beliefs. Nobody chose that one. I can see 12 out of 17 chose the proportion of patients fully recovered. How many days until recovered is not really something we're dealing with. We talk about after 3 days. It is a parameter for something, for the measure, but we don't have anything else about it. And the amount of medical records, it's more like our N. So you would probably see that for the value we use for the 80% is the P. It's a belief. It's not a sample that we have right now. It's not calculated on top of the 20 medical records. It's a belief. So it's our population mean. And the 20 medical records, it's our N. It's the size of our sample. So sorry, let me share here. Sorry. The answers. So you will see, since it's a belief, it's more like a population. Therefore, the 80% is more like the population proportion. I said mean, sorry, it's a proportion, P. And the random sample, then it's more this light blue or greenish blue, which is the 20, then it's the little n, okay? I'll stop sharing. Let's get going with this one. Or not. We will have another poll. So these are the variables we have. Variable of interest, proportion of patients recovered, N equals 20 households, P equals 80% or 0.8. Remember, we're always using 0 point something, like between 0 and 1 for proportions in our calculations. So can we do a Z transformation in this case? Let's check. I will give you all the numbers and the things we have to check, and we will have, let me have a look if there's anything on chat. Nothing. We will have another poll, and I'll give you guys a chance to calculate finally as the last, kind of the last poll, definitely the last poll we're doing in this tutorial. Let's calculate. Give me an answer, yes or no. Is P equals to 0.5? If not, is N times P bigger than 5? And is N times P minus 1 bigger than 5? And if these two things here are true, then we can do a Z transformation. If both of them at the same time are true, then you can put a yes. Or, I mean, if that's a yes and that's a yes, then the last question, the fourth, is a yes too. If one of this is no, then the last question, can we do a Z transformation? No, it's a no, okay? This is a little bit shorter one. We already have 17 answers. I'll give you guys another maybe 5 seconds. 19, almost everybody had it. 20, amazing. Thank you so much for your answers. 21, 22. Okay, that's it. And poll, excellent, guys. Share results. So let's go. Is P equals to 0.5? No, we already have the population proportion. They mentioned 0.8. So it was a split 50-50 for yes or no, but it's a no. And I will have a click here to show you guys the answers. Then is N times P bigger than 5? It is 20, the number of households we have, times the 0.8, it is. But the other one, 1 minus P, it's pretty small, 0.2. And when you multiply, we only get 4. So this is a no. We cannot do a Z transformation this one, which is tricky because I think every single question we did up to now was a yes. So finally, it's a no. And this can happen in your CML or LBRT. I can see we had 14 out of 22. So 64% of answers saying yes. And that's because we had 73 yeses for the first one, which is correct. And 55% saying yes for the no, which is incorrect. So it is a no. I'll stop sharing. Very good job. Tricky question, but it's very important for us, if by any chance you got it wrong, to do it during the tutorial, because it doesn't affect your grades right now. Then you can do it correctly in your CMLs and LBITs, okay? Thank you for participating. So let's go. So what's happening here? What can we do about it? Usually, the belief from the doctor is not something you go there, oh, I want to believe it's something else. Let's not believe 80% anymore. Let's believe 90. No, that's not what we're going to do. But we can change the sample size. So instead of looking at 20 medical records, we can look at a few more, expand our sample, so we can be a little bit more precise with what we're talking about. All right. Let me see. I'll just open the chat before I go to B to see if someone asked anything or said anything. No, all good. So let's go to B. Here it would be a little bit of explanation. What can we do? We can change the size of the sample. Now, B. If the sample of patient records is increased to 80, what is the probability that the sample proportion will be within 0.1 of the population proportion? Use P equals 0.8. Yeah, that's pretty much what we're doing here. So 0.8, we want 0.1 each side. So minus and plus. Let's see how it looks. So when we subtract 0.1, we have 0.7 here and 0.9 on the other side. We want to use both of them. So I'll get going. Can we do a Z transformation in this case? We're very close to do with 20, so I'll just go ahead with this one. We can, because now with 80 observations, we get 64 and 80 down here, we get 16, both above 5. So we can do a Z transformation. And I'll get going because it's 5:21 now. So let's finish this last exercise. Z transformation, let's move the things here. This is the Z. And look at what we did. We're using this the first equation, and we will put both sides first. We calculate for this new sample size. We're calculating a new sample standard deviation, sigma b hat, and we get 0.04472, which will be used here and here. So 0.7 to one side, 0.9 to the other side, smaller and bigger. So 2.24. I will ask your help for our last thing today. Let's look at our Z table. Can I please have on chat the value for 2.24? Excellent. Very good, Harry. Good job. Thank you, Jesna. Thank you. Very good. So yeah, that's what we have. 2.20. Oh, that's horrible. 2.20 for 48.75. So it's the same size both ways because it's a minus 2.24 and then it's a plus 2.24. So we just add the value, put the value twice and add because they're in different sides of the mean, and we have 0.9750. And that's it for this week's tutorial. Thank you so much for your participation. We had a lot. It was great. So we were talking about describing the characteristics of sampling distribution for sample means and sample proportions. We talked about how it works, explained the importance of the central limit theory, and sometimes we can do the Z transformer, sometimes we can't. So it's important to have a check, but it's a very good assumption since a lot of times we don't know the distribution of our observations. So then calculate Z-scores for particular values of the sample mean or sample proportion, and finally calculate the probability of obtaining particular values of the sample mean or sample proportion. So if you guys haven't yet, good luck with your second attempt for LBRT2, and good luck with CML03. Thank you for joining, and I'll see you next week. I'll stop recording.